about hidden sector dark matter, and in particular, in the context of what we've been hearing all morning, really thinking about why it is we should start thinking beyond the WIMP paradigm, focusing in how the different methods that we may search for it. Okay, so as we've heard a couple of times already this morning, one of the most compelling reasons to look for dark matter at the weak scale, besides solutions to the hierarchy problem and so forth, is because the dark matter density fairly naturally just comes out of it. So if I have my universe here, and this is not showing up very well, if I have my universe here, two dark matter particles come in, they annihilate until there are so few of them left anymore that they can't find each other. I can compute from just the observed energy density of dark matter what the annihilation cross-section is to account for all the dark matter in the universe, and you find roughly that the weak scale just comes out of this problem. And so as a result, we've been going after looking for the WIMP, and one of the primary ways that we have been doing this is in direct detection experiments. And direct detection experiments quite literally are just classical billiard ball experiments, at least from a theoretical point of view. Dark matter comes in, it interacts with the target nucleus. Target nucleus recoils away from you, and if you put in the velocity of the dark matter, which is 200 kilometers per second, roughly speaking, about 10 to the minus 3 times the speed of light, what you find is that a typical recoil energy of this target nucleus in this classical billiard ball experiment is on the order of tens of keV. And that's the scale that direct detection experiments like PandaX, like LUX, like LZ, like Xenon 1 ton, like CDMS, that's what's been driving their experimental prospects for detecting this stuff. Now, even though the WIMP has not been ruled out, and in fact it won't be ruled out, I would say it's fairly safe to say that this paradigm of the WIMP is under assault by the amazing sensitivity in these dark matter experiments. So strictly speaking, dark matter interacting via the Z boson, if you just do a naive back of the envelope calculation, gives a cross-section that's orders of magnitude ruled out by now. So it predicts 10 to the minus 39 centimeters squared, sort of back of the envelope. And where we are right now in these direct detection experiments is that they're probing down at the 10 to the minus 45 to 10 to the minus 46 centimeters squared kinds of cross-sections. What we're going after right now in these experiments is Higgs interacting dark matter. So that's really the sweet spot in the center of this red blob, which experiments like Xenon 1 ton, LZ, PandaX are going after right now. Now there's, below this, there's some sense in which we're entering now the LEP phase of dark matter direct detection experiments. They're sensitive not only to tree-level scattering cross-sections, but to also one-loop suppressed processes. So for example, if I have Higgsino or Wino dark matter exchanging a pair of gauge bosons, for example, you can calculate that, and depending on what the nature of the candidate is, for example, if I have a pure Wino dark matter candidate, I can compute the size of that cross-section as a function of the Higgs mass, and it tends to predict scattering cross-sections were about 10 to the minus 47 centimeters squared. And you can see that that 10 to the minus 47 now is also within reach of an experiment like LZ. So even though at tree level, the scattering cross-section can vanish, I can still see it. These experiments are becoming so sensitive that they can even pick up one-loop suppressed processes. This plot shows that Higgsino dark matter has this unfortunate cancellation, and this is from a single nucleon interaction. We'll see if two nucleon scattering processes can actually move that cancellation away from where it's currently at. Now, absolutely, we should continue to push down to smaller and smaller cross-sections down to where we'll start seeing atmospheric neutrinos, but you're going to start hitting more and more experimental challenges. We've been a little bit spoiled over the last decades that we've really had a Moore's law of sensitivity just pushing down orders and orders and orders of magnitude to smaller and smaller cross-sections as time has gone by. But the time is coming, not so very far away, where we're going to be using a non-trivial fraction of the world's supply of xenon, for example. So these experiments, as they become tens of tons, they're going to become more and more challenging, obviously. And so I'm going to be talking about dark matter targets that are very well motivated, that don't live in this favored WIMP mass parameter space. So we can ask the question, as you go to lighter masses, for example, what kinds of dark matter candidates live out here at lower masses? And how is it that I build experiments to look for them? Because the technologies that we've developed and we've focused on have really been aimed at going after recoil energy that are in this 10 keV range and that satisfy the sharp predictions of the WIMP paradigm. And I want to begin by arguing that it is very easy to write down dark matter candidates that I can detect with not a ton year or 10 ton years or 100 ton years of exposure, but which I can get with a milligram year exposure. Okay? So these are very small scale potential experiments that go after qualitatively new types of dark matter candidates. And the paradigm is that of a hidden sector. So the idea is that rather than the dark matter carrying electroweak charges, being like an electroweak doublet or triplet, the idea is that you have the standard model, there's some connector particle, which may be charged under some new gauge group, for example, or it might be a scalar particle. There are a number of different models you can write down. And that connector talks about the standard model and the dark matter. But within this paradigm now, there's no particular reason why the dark matter has to be at the weak scale. So it could be the case that if I look at the universe, the visible universe in its ground state at lower energies, what we have been accustomed to doing is accelerating particles to higher and higher energies. So we're looking in the peaks. We've looked for the Higgs boson. We're looking for supersymmetric particles. But it might be the case that what we're really after is in some other low mass hidden sector, in some valley, in some other potential different vacuum. And that the way that we would produce it is through either accelerating to the high energy peaks or looking for it in a low energy type intensity experiment, which is what these direct detection experiments really are. And let me just give you an extremely simple example of this. So in analog to the standard model, I could have accidental symmetries in my dark matter sector, and that could stabilize the dark matter. So we have examples, we have baryon and lepton number in the standard model. Well, there could be some analog of that, like a dark pion. And let's suppose that there's no weak force. So I have an isospin symmetry now that would stabilize the dark pi plus. It's electrically neutral. Okay, but now I have a very simple mechanism for setting its abundance. For example, I could have a particle-antiparticle asymmetry, so a small asymmetry between the pi plus and the pi minus, and they could annihilate to pi zeros. Those guys you could get rid of, for example, by decaying back to the standard model, and then I would just be left with a small abundance of pi plus left over at the end of this process. Now there are a large range of models. Once you think about this paradigm, I just gave you one very simple example. There are a huge range of models that I can write down. So here again is the standard model vacuum over here. Here would be some dark sector. There's some connector here that is shown here as a barrier between us and the dark sector. There are a broad range of models that I could write down and in fact have been written down. And so I think one way you can proceed is to start thinking about, well, what are some benchmarks and how is it that I go after them? So one class of models that people have started going after is asymmetric dark matter. So one of the reasons why this is nice is because, first of all, it's within reach of the current technologies that have been built. So if you had a cartoon, again, dark matter, mass and scattering plane ruled out is up here in the current searches. Generic WIMPs, say, would lie in this blue blob. Asymmetric dark matter is a candidate where the natural mass scale tends to be not so far from the proton mass. It's not a lockbox, but that's sort of a general mass scale that comes out. And you can write down in a theory where you set the mass scale, say, by supersymmetry. And it predicts a scattering cross-section. And you can see that this is just below what is currently reached with the set of dark matter experiments that exist. And the bottom line reason for why it predicts a scattering cross-section is actually an analog to the standard model. So in the standard model, we have electrons but not positrons. How do we get rid of the positrons in the early universe? We take E plus E minus and we annihilate to photons. Well, there could be exactly the analogous process. In the dark sector, I have a small amount more particle than antiparticles. So this again is the visible sector. This is the dark sector. I have slightly more dark matter than anti-dark matter. and I get rid of the anti-dark matter by annihilating dark matter and anti-dark matter against each other until I have only this small part, 1 part in 10 to the 10 asymmetry left over. And so this would very naturally imply the presence of dark forces. And now those dark forces become very natural mediators, and in some cases they're predicted to give rise to a scattering cross-section, which you can look for in a direct detection experiment. So this is all great in terms of targets that we can go after right now, but you find out very quickly that our current methods of looking for dark matter, when I start to think about hidden sectors, become limited. And there's a very basic reason for that, having to do with kinematics. So again, going back to your elementary school billiard balls, dark matter comes in, it transfers some momentum transfer. The amount of momentum it can transfer is at most its own velocity or its own momentum. And then you have the target nucleus that suppresses the total amount of energy deposition in the process. So let's imagine I go below the nucleus mass. So now dark matter is dropping below 10 GeV. It's, say, closer to an MeV. So let's look and see. MeV dark matter would has a total amount of, so let's suppose I have sensitivity to electron volt energy depositions. That corresponds to dark matter mass, which is about 300 MeV. So if I was just going to look through nuclear scattering processes, I actually pick up a very small fraction of the dark matter kinetic energy because of the fact that I'm suppressed by the ratio of the dark matter mass to the nuclear mass. So if I'm going to go well below GeV dark matter mass, I really don't want to be using nuclear recoils anymore. So the next simplest thing you can do is just to say, I'm not going to use the nucleus, I'm going to use the electron. So now that allows me to get all the way down to MeV mass dark matter to collect all of that kinetic energy, which means that if I have sensitivity to now EV energy depositions, that implies just by MV squared that my sensitivity to dark matter corresponds to about a mega electron volt. Okay. And in fact, dark matter experiments have already started constraining dark matter models in this region. Okay, so Xenon 10, for example, I think did the earliest analysis looking at electron recoils. So the idea here was that dark matter could come in and it could just rip off an electron from a xenon atom. And so what that allowed them sensitivity to was 10 MeV dark matter. You can see that right here. So the point here is that 10 MeV dark matter carries 10 electron volts of energy, roughly speaking. And that corresponds to the approximate ionization energy of an electron in xenon. Likewise, in semiconductors like germanium and silicon, super CDMS right now is looking to go after exciting electrons to the conduction band, and then collecting those ionized electrons through the Lukneganov phonons, through basically gaining the process. And so they're hoping that they're going to have sensitivity now to 1 MeV dark matter. I just want to point out here, this is 10 to the minus 38 centimeters squared cross-sections. Super CDMS with 10 kilogram year exposure potentially could get down to the 10 to the minus 43 centimeters squared. And what I would like to emphasize is that in contrast to what's happening with WIMP searches right now, where we're focusing on 10 to the minus 47 or 10 to the minus 48 centimeters squared, there are interesting dark matter candidates that satisfy all of the current constraints and are simple extensions of the massive dark matter paradigm that give rise to scattering cross-sections that are in this range. So there have now been a whole suite of experiments that have been proposed. Now, again, I'm pointing out this is the MeV scale. So this plot now starts where the WIMP plot ended. So now we're extending down to 3 orders of magnitude. The solid line is an experiment like Sensei, which is actually in R&D right now. And these yellow lines are, I should say orange lines, are theory curves for what these experiments can go after. Okay. So this is an active, ongoing area that's really exploding. There's an enormous complementarity also with accelerator experiments. So these are low energy accelerator experiments. Now I can have an electron beam come in, interact with a nucleus, and it can, for example, radiate off a dark photon. And these orange lines now here correspond to the same orange lines on the previous plot. This is an experimental proposal, LDMX, and you can see that in the same mass range, it can also probe some of the same region. So this is just the start, in my mind. So the traditional WIMP experiments have been focused up here at 10 GeV and heavier. Semiconductor experiments like Super CDMS, like DOMIC and Sensei, are now pushing down into this 1 MeV mass range. But there's an entire range of candidates, most of them non-thermal, that naturally populate this region of parameter space now that's below an MeV. And so the question becomes, how is it that I go about looking for them? Okay, so all of these targets that are currently being used right now, at least in their current modes and their current setup, have a fundamental limitation that doesn't allow them to go below an MeV. So how is it that I can start to probe some of these other dark matter candidates? Well, one very simple extension of these same ideas is to use a smaller gap material, like a superconductor. So superconductor is a normal metal at low temperatures. And so what happens as the temperature in one of these metals drops is the electrons succumb to collective dynamics. They pair up into Cooper pairs. And the typical binding energy of the Cooper pairing is about 1 millielectron volt. So going back to this previous slide, EV energy resolution corresponds to 1 MeV or heavier dark matter scattering. Milli-EV energy resolution corresponds to this KeV to MeV range. And there's an additional process whereby I can actually absorb a dark matter particle that allows the same set of experiments in the 6 orders of magnitude between KeV and GeV to probe a different class of dark matter candidates through a different process, through an absorption process. So how does this look? How does an absorption of a sub-EV dark matter candidate work in a target like a superconductor? So the idea now is you actually have to take advantage of collective modes. So you have to actually take advantage of the phonon modes in the material. So the idea is that the dark matter candidate, so let's say it's a dark photon, comes in, it has an extremely small interaction with the electron, and then it breaks the Cooper pair and it kicks out a phonon in this process. I can quantize this theory, work out the implications for a dark photon, and now I'm below a KeV. Okay, so before we were up above a KeV, now we're looking at actually 100 EV and below. And these two curves here, the blue curves, correspond to what a superconductor can do with just the kilogram year sensitivity. Okay, and you can see that it cuts into parameter space that is not constrained by stellar observations. And you can see the size of the couplings that are probed here are absolutely tiny. So we're talking about effective couplings that are 10 to the minus 12, 10 to the minus 13, and so forth. You can also use semiconductors through a little bit more complicated process because you have to get around the gap. You can now actually take this phonon that you've produced and spit off a couple of other phonons through an anharmonic process. And in semiconductors, that also allows you to probe the same mass window below an EV, and also in qualitatively new parameter space. Once you've started thinking about what collective modes can help you do for dark matter detection, there are a whole slate of other materials that open up. So one very nice material for dark matter detection is superfluid helium. So superfluid helium is nice as a dark matter detector for one reason, is that any noise that propagates lower than the speed of sound in the material simply does not couple to the material. So in superfluid helium, that's about 10 to the minus 5 times C. And so it actually tends to be a very nice self-damping kind of material. Okay? And in fact, there are already groups that are looking for ordinary dark matter recoils in superfluid helium. But if you want to detect very light dark matter, you actually have to couple directly to the phonon modes. Now, at first glance, it looks like superfluid helium is actually going to be very poor at coupling to dark matter. And the basic kinematic reason for that is that the dark matter velocity is about 10 to the minus 3 times C, whereas the speed of sound in superfluid helium is about 10 to the minus 5 times c. So if I look at that in a dispersion plane, so here is the momentum transfer in the process. Here's the energy deposition. So just to convert this into particle physics units, this is on the order of keVs of momentum on the x-axis, and this is on the order of millieVs of energy on the y-axis. Phonons have a linear dispersion and tend to lie right along this diagonal line, whereas dark matter tends to deposit energy along this y-axis. And so there seems to be a momentum mismatch. But that's until you take into account the fact that there are anharmonic modes in this material. You can again quantize and now populate this entire dispersion plane by spitting off multiple phonons. And the nice thing about this material is that this curve right here is actually a renormalized phonon. So the fact that I've measured this very well actually allows me, using renormalization theory, to actually go and just compute the probability for a dark matter particle to come in, deposit a certain amount of energy and momentum on the helium nucleus, and now spit off two basically back-to-back phonons in order to couple my dark matter particle into the superfluid helium. And what this allows you to do now is to look beyond ordinary nuclear recoils in superfluid helium. So here, dark matter mass is in MeVs. The gray line here is what you can do with ordinary nuclear recoils in superfluid helium. Now, if I also add in these anharmonic processes of spitting off multiple phonons, this allows me to dig into more parameter space, more mass parameter space to lower masses. And the thing I want to point out again here is you're sensitive to really, really tiny couplings. And this is not a huge exposure. This is a kilogram-year exposure. So in many cases, depending on the dark matter candidate, you can again probe qualitatively new regions of parameter space. And in my couple minutes left, I just want to make a few more comments on specific targets that you can go after. So here's another material. This is a Dirac Semimetal. And the thing I want to emphasize here is we're leveraging the enormous progress in condensed matter physics. So now they're at the point where they can quantum engineer materials. And the unique thing about these Dirac semimetals is that if you look at the band structure of the material, you can see that there are bands in this red region here that cross the Fermi energy. And at that point, you have a small gap in the material. Small gap means I have sensitivity to very small energy depositions. You say, okay, so what? Does that mean I can go after interesting dark matter candidates? And the answer to that is yes. Okay, so here again is dark matter in the keV mass window. And here's the scattering off of an electron. I want to draw your attention to a band here where dark matter is populated by a freeze-end process. So the coupling of the dark matter to a dark photon is about 10 to the minus 10 in that range. And it predicts a scattering cross-section in these direct detection experiments, which is this orange band. And down here is the sensitivity of a semimetal with a kilogram-year exposure. Okay, so you can see that this is approximately 6 orders of magnitude, 5 to 6 orders of magnitude below this prediction for dark matter populated through freeze-in. And so you can probe this new region of parameter space, these models, by just having a milligram-year exposure. Okay, so this is a different, entirely different kind of dark matter candidate that you can probe with very, very small exposures. And something I would like to emphasize is that it's a qualitatively different in the sense that these guys tend to be very, very feebly interacting with the standard model. So I've been talking about couplings which are 10 to the minus 10 or 10 to the minus 12 or 10 to the minus 14, which are non-thermally produced, so you don't run it afoul of any Big Bang nucleosynthesis constraints on the number of light degrees of freedom. But nevertheless, because you have a direct detection experiment that sits at very low momentum transfer and can just integrate, okay? You don't have to run a beam. We have a cosmic beam, the fact that we're moving around the center of the galaxy, that provides the dark matter for us. And we can probe this entire region of parameter space through these new techniques. Okay? And it has complementarity with this other region of parameter space where dark matter tends to be produced thermally and is probable by the more traditional types of direct experiments. So I'm just going to conclude for lack of time. So the road forward. I've talked about many different ideas here. I'd like to emphasize that we have not drunk this well dry, both in terms of thinking about what kinds of candidates, target materials would be good for looking for these candidates, and also in terms of building new types of models that would appear in these kinds of experiments. And they're not hard to write down these theories. In fact, you could argue that additional vacua, hidden sectors, are quite generic in many top-down theories. Okay. But we do have to move beyond sort of this standard idea that we should look for dark matter through nuclear recoils. That's been extremely successful. I completely agree with the sentiments of the previous speaker that we need to push down to the neutrino background. We should keep going after that. But that program has momentum, is funded, and is being pushed through. This program is just getting started. Target diversity is really essential because they probe qualitatively different kinds of dark matter candidates. So for example, superfluid helium is terrible for a dark photon, but semimetals are amazing. But for other types of dark matter candidates, semimetals would be terrible. What we're really doing here is leveraging enormous progress in materials and condensed matter physics. This experimental program is, I would say, 5 to 10 plus years into the future. There has been an explosion of interest in the community, and there are experiments now that are getting underway. The payoff for all of this is that we're going to get, if you say we're at 1 GeV sensitivity right now, you're going to get down to keV mass and scattering, and potentially all the way down to milli-electron volt in absorption. So you get 12 orders of magnitude in dark matter mass reach, but a long view is necessary. So if we think of this in terms of a comprehensive dark matter search program, even if there were a signal that would show up in a ton scale experiment looking for WIMPs, that's not to say that the dark sector isn't complex and that there might be other candidates lurking elsewhere. It really would just be the start of this road to understanding what's living in the dark sector. So I'll stop there. Thanks.
Great. Do we have any questions?
So can you go back to the semi-metal?
Yeah. Yes. Yes.
So is this using scattering or absorption? Like I didn't get the
This here is scattering.
Oh, it's
So
so
this could also probe absorption, and it has a very nice reach for dark photons. But this particular case is scattering. So it's actually a word identity. So semimetals have an absolutely terrible density of states. So naively, you would expect that they would just fail in comparison to superconductors, which have this giant Fermi surface. But the thing is that superconductors you can think of as actually violating Lorentz invariance in the sense that they have this giant, the electrons have a Fermi velocity. And so they actually have a big and medium effect, and that turns out to suppress the dark photon interaction rate. These guys now, when you expand around that Dirac point, it actually behaves exactly like free QED. And there's a word identity that protects the polarization function. And so it's Q squared suppressed. It behaves just like renormalization of electric charge, exactly like that. And so it doesn't pay this penalty for looking for a dark photon. And so that's the reason why it's so, semi-metals are so amazing for dark photons. Yeah.
I have a qualitative question about backgrounds for these, and I mean, of course, you didn't have time to talk about backgrounds so much, but when you're looking for nuclear recoils, you're looking for this tiny nucleus recoiling, and so to get the signal, something sort of small and massive had to hit it, right? So that's already, you're already winning because you're Whereas all of these things are very, very low energy, right?
Yeah.
So why don't you have to worry about everything in the world triggering all these processes, which is something we don't have with nuclear recoils?
So the answer is that certain kinds of backgrounds, like radiogenic backgrounds, tend to get better because you go below them. The things that you worry about in these experiments are what goes under the generic name of parasitic power. Basically vibrations. So that's, if you want to call that everything in the world, the answer is yes, you do. So Super CDMS has a lab in the basement, and they actually see the students come out of class because they all turn on their phones, and that's a background. Seriously. And you can tell the difference between an iPhone and an Android because they have different kinds of signals.
This is not comforting.
Well, the remarkable thing is that Super CDMS thinks that they can control vibrations and thinks that they can actually suppress those couplings to everything in the world. So if you think about it, I mean, what has LIGO done? They've actually dealt with everything in the world. And so if you talk with, I will grant you optimistic experimentalists, they think that this, with 5 to 10 plus years of work on specifically dealing with these kinds of backgrounds, that they can get there.